Hi, this is Nick, and this is a short introduction to calculus. And disclaimer up front, I'm targeting this towards people who have probably had some calculus. They know some of the mechanics, but they're not really sure what it all means, how it all goes together. So this is not a bare bones introduction. If you've never done calculus, this may not mean as much to you, but if you know the mechanics, you know how to take derivatives, but you're wondering what the heck is all of this about, that's what I'm going to try to address here in a short video. So a lot of calculus is based about the concept of motion, right? And so imagine that you have something moving and its position, s, is given by the square of how long it's been moving for, okay? So this is typical of something that's falling under acceleration due to gravity. It moves farther per second after 10 seconds than in the beginning, right? It accelerates, it picks up speed. And so we can make a table of how far this object moves at different times. So at time 0, it hasn't moved at all. After 1 second, it's moved 1 unit. After 2 seconds, it's moved 4. After 3 seconds, 9. 4, 16, and 5, 25. Now, my mantra about calculus is the following. Algebra is about pictures, calculus is about movies. Okay? Algebra lets you take a snapshot of something and analyze it. And we can take lots of snapshots and look at them one after the other and get an approximation to a movie. But if we actually want a movie where things are moving in a continuous way, that's when we've moved from algebra to calculus. So let's apply that to studying the system and ask, how fast is this particle moving? Well, we know at time 0 it's not moving at all, right, apparently. But let's just look at it across this distance of 5 seconds and say, how far has it traveled in 5 seconds? It's gone 25, let's say, feet. Okay, 25 feet in 5 seconds, that's 5 feet per second. Okay, that's what we would call its speed. So its speed equals 5. We're just going to stick with feet per second, okay? 5 feet per second. Well, that's a snapshot view. The thing started at a distance of 0 at time 0, and 5 seconds later we take a picture, and at time 5 it's moved 25 feet. Okay, what can we say? It's moving about 5 feet per second. But let's look at this a little closer. Let's look at what happens in the first second. So in the first second, it moved from position 0 to 1, and it took 1 second. So 1 second, it moved 1 foot. How many feet per second is it? 1 foot per second. So its speed here was 1. Now let's just look what happens if we take a snapshot here at t is 1 and here at t is 2. In 1 second, it moved from position 1 to position 4. It moved 3 feet. So for this second, it looks like its speed was 3 feet per second. And we can do this for each of these points in time. From time 2 to 3, that's another 1 second interval. It moved from 4 feet to 9 feet. That's 5 feet. So here it looks like it's moving 5 feet per second. And from time 3 to 4, it moved from distance 9 to 16. That's 7 feet per second. And from time 4 to 5, 16 feet to 25 feet, that's 9 feet per second. So if we just took a snapshot at the beginning and the end, it looked like it was moving 5 feet per second. But if we take 5 snapshots, we see different speeds at each snapshot. First it was moving at 1 foot per second, and at the end it was moving at 9 feet per second. So what is the speed of this object? Well, if we look at these numbers, some of them are smaller than 5, some of them are bigger than 5, the one in the middle is 5. If we were to take these averages, right, add these up and divide by 5, we would get 5 feet per second. Okay? So this is a good average figure, but we can see that, sometimes the particle's moving slower, sometimes it's moving faster. So the question is, what actually is the speed of the particle? Well, right here, it looks like it's moving 1 foot per second because it went from 0 to 1. But let's take a tiny little second later, 1.01 seconds, and I'm going to use my calculator to square that, and I'm going to see the distance it would move is 1.0201. And so in the time from here to here, which is 0.01 seconds, how far did it move? 0.0201 feet. Well, if we divide that by 0.01, the decimal points are confusing, but this will turn out to be 2.01 feet per second. So now we've got a new number, right? At time 1, it looked like it was moving 1 foot per second, but if we look at what it did between time 1 and 1/100th of a second later, it's actually moving pretty close to 2 feet per second. And we can do that at different places. If we look right here at time 3.01, and I'll use my calculator again, and see that this would have moved a distance of 9.0601 feet. Well, that's a distance change of 0.0601 feet in 0.01 seconds. Well, that's 6.01 feet per second. We got lots of numbers going on here. What is going on? The reality is that by looking at how we change distance over a space of 5 seconds, we got a very approximate number. It's an average, 5 feet per second. By looking at how far we've traveled over a distance of 1 second, we got different numbers, 1 feet per second, 3 feet per second, 9 feet per second. That's a better approximation of how fast we were moving around this time, or around that time, or around this time. But the smaller the time that we look over, the more accurate our answer is going to be. If we try to measure our speed over 5 seconds, we get a pretty crude number. If we try to measure our speed over 1 second, we're getting a better number. We can see that we're accelerating. We're going faster over time. But if we take our calculation over 100th of a second, from 1.00 to 1.01, what do we get? We get a very different number. We get approximately 2 feet per second, 2.01 feet per second. And out here at time 3, we get 6.01 feet per second. All right. So this is what calculus is. It's taking this to an extreme and saying, suppose that we took this measurement over 1,000th of a second. So at 1 second, we're at 1 feet. At 1.001 seconds, my formula on my calculator says we would have gone 1.002001 feet. So the total distance we traveled is 0.002001, and the total time was 0.001. And if we do that division, we end up with 2.001. So our first estimate was 1 foot per second. Our next estimate was 2.01 feet per second. Our next estimate, by looking only 1,000th of a second past this point, is that we're moving at 2.001 feet per second. Okay, this is where the concept of a limit comes in. A limit just says keep doing this but get to a ridiculous extreme. Suppose we were to take the distance at time t equals 1, and we see that our distance is 1, and now time t equals 1 point, and let's just make this a slight amount of time further in the future. Our distance is going to be slightly bigger than 1. But if we look at the change in distance over the change in time, we're going to be really close to the number 2. Okay, so we can talk about the limit, meaning if we were to do this to where we moved so small an amount that it was effectively not moving at all, right? The ratio of how far we would have moved versus how much time it took would be about 2. And calculus is a way to do this systematically, mechanically. Because in calculus, what we'll find is that if we have an equation like s equals t squared, we can find the change in s with respect to time, and our formula for differentiating polynomials will tell us it's equal to t. Well, that's what we're seeing here. If t is 1, this says that change in distance over time should be 2. That's that limit we're getting to. If t is 3, this formula tells us the speed should be 2 times 3 is 6, right? And that's the number that we're getting here, 6 feet per second. So this whole business of a derivative is just doing this in the extreme. It's saying suppose you're at some point t and you move slightly forward in time, how does your distance change relative to that change in time? And if we move small enough, we'll see that that ratio is really, really close to 2 times t. That's the sense in which this is the derivative of t squared.